this is again for whatever reason called initial data deletion. Okay. So now what we do is we have, so we run the same experiment m times, so there are m replications with n observations. So in the case of M1 we would say until the 500th customer complete service, run it, right. So n say equals 500 means I want 500 consumers to have completed their the processing in the system, right. So that is why n, it is not time based, it is the number of observations that you make, number of samples that you are collecting for whatever metric that you are measuring. Okay. So you have m replications each with n observations. So you now have like this big table of values, right. So this is first replication, first value 1, 2 and so on up to 1, and then you have the second experiment or second replication, so that is your set of values that you have collected from your system so far. So this is like post processing, right. You are not really trying to delete at that instant, you are processing this post facto, and then you are trying to see what should, where I should simply drop off the steady state, the transient state of the system. Okay. So then now let us compute xj, which is this average. So I am computing, this is your jth observation, right. My j goes along this axis. Yes, no, each with n observation. So example, if I say run it 10 times, I run my simulation, right, MM1 with 200 customers each, right, 200 completions, I will say 200 completions. Okay. So the first completion, second completion, that is when I do my measurement, right. I will compute delay only when the customer finishes service, so that the completion is when I start these metrics, this particular metric at least, right. Other metrics utilization I can compute any time, but delay I would compute only when there is a completion, right. Okay. So my j basically goes along this axis, right. So j is increasing order of the number of observations, so xj is gonna be xij and then we compute the overall average, which is because I am only looking for one value, right. I just want to know what is the average delay. For that I have got mn values to choose from to give me better, right. Overall system metric only is only one value metric, right. X is in this case, yeah, whatever x is, x could be the average waiting, average service time at every instant, every observation that keeps getting updated, right. So at the end of the first customer, the average waiting, average service time, average time in the system was say 1, and then it goes to 3, and then so on, right. So each x is could be a mean also. Okay. So now we will come to all your, yeah, xj, no, xj is basically this one. When j equals 1, I am looking at the average across all the m replications.
Should be divided by
yeah. Oh. So now L is the value we want to find out, right, that delete. So let that L be whatever it is. So we delete first L observations. So L can go from anywhere from 1 to n, right. So for a particular value of L, we compute, let us go to the next slide if this is going to be. Oh, sorry, there should be a bar here, bar there. So, if I ignore the first L observations, then I compute this XL bar. So, this is sort of like your running window, right. So, you are excluding L first L, then computing what should be the mean of the remaining observations. Okay. Then you compute the relative change, which is for given L. Which is basically so would this be always positive? Because I am excluding the first L values, and then this is the overall mean, this is the subset of the mean. So it need not be, right. So there should be a modulus, there should be a magnitude, magnitude along here. It does not have that. Okay, let us assume that there is a magnitude, but essentially what we are looking for is at some point in time, right, your XL and X bar should be close to each other, right, which means that anything below, so if an XL bar equals X bar or comes close to X bar, you know that this is the steady state of the system, right. Anything below that, there is too much variation, therefore I should can safely ignore that. So that is kind of what this approach is trying to do. So if this is L and you plot this value here, this change, it is supposed to sort of, initially the rate of change will be higher, at some point in time your rate of change will be slowing down. So at the point at which this at the knee of the curve, you would say this is the value that I want to delete. So this is transient, right. So I am doing this for every L. L equals 1, I compute XL bar minus X bar, or XL bar bar minus X bar bar. So this is with replications though, right. With replications is in fact this used to be part of my assignment 2 last year. Last time I taught it, this time I removed it, I saved you that. Otherwise we had to actually just implement this and then start the similar or exclude those values, right. So right now in this Yaxim code there is one thing called set deletions, some of you might have seen that, right. So I am just doing it manually, set deletions 15 and just ignoring or 5 is what we normally do, because we are doing batches, so first 5 batches we tend to remove, but this is a little bit hopefully, right, cleaner way of trying to find out when the system is going into steady state.
You know that if you use range, that you know that there are something like range charts and things like that, which can be used to again get what is the control that we have.
So this will be the
because
range.
X bar will make sure that we have extremal values, then X bar will still be the same, but it is still a transient state.
Okay, I have not looked at range based control, no. Yeah. So that is looking at the range of values itself, or is it
so in the replication you can look at the range of values that we have.
Okay.
If the range is very large also, that is also not
indication
correct.
of that there is wide variation.
There is wide variation, so that is also transient.
But this would be but okay, so again you have a window of value, same thing, you instead of looking at the mean you just look at the range. Okay, so if I keep changing this value L, and you compute the range, simply the range of values for each of these, and then the one with smallest range, or how do you compute?
Basically, range also has, like here what you are trying to do is
They are looking at the range, the control. Okay, okay.
we're trying to make sure the variation is not so high. Same way we can look at the range and we can see that whether the range is under control. Once we have range under control, for
Then
some
you
of
can,
this thing,
okay, then you
see
can
that
stop
it is
it.
controlled here.
Yeah, I'm not.
When this graph goes up to infinity, so like
This will be a n technically.
up to n. So will it again come back to 0 because it will be
If it is steady state, if it is the steady state, then your then what is happening is, okay. So your x bar is actually including all the values, right?
So then in that case, xl double bar will be equal to x double bar.
That is, but again, that's going to be hard to say that. Just that.
But you are looking at average rate.
Yeah, it should. Yeah.
No, the system is not.
This relative change, but see, the thing is that x bar is actually including all the values, and your xl bar is actually subset of the values.
It will become 0 square. So it will become.
It will not. Yeah. Okay. You're saying that should it. Yeah. Yeah. Actually, yes. Sorry. Then that will go to 0. Yeah.
The graph will be inverse. It will start from the value of 1 because at L equals to 0 or L equals to 1, it will be
higher. It will be the other way around.
Yeah. The value will start from 1, and as XL approaches its x double bar, the graph will asymptotically be 0.
Or there is an XL bar in the.
XL double bar approaching.
Or it will be XL bar in the denominator. In which case it will go towards 1. But no, sorry, it will go to 0. If XL bar equals X bar. So there are a couple of other techniques which again use the same business of replications and so on, which I will skip for now. So then you have your independent moving average. So the two schemes are there. One is based on independent replications, and this is very similar, right? So I'll just let you read that. And other approaches where you run the simulation for a very long time, but you break it up into smaller batches, and then look at the batch by batch means, and then you try to converge based on the batch means, right? Which is what this driver auto terminate actually tries to do. It is based on batch means, where you have right, you compute, say, every 500 customers compute the delay, every 500 customers compute the mean delay, and then you find whether the mean delay is essentially overall, right, converging. At what point does it start converging? And you say at this point there is no need to look at that is your transient state. And the same thing is also used for termination condition, where if you look at the variance across the different means, if that is going to be very small, then you know that you are more or less approaching steady state, or there is no need for running the simulations much longer than this, right. So in batch means what you do is you have the same set of n observations, you are only running, right, there is no replications, only one run. Okay. Then you have a total of n observations, right. Then you define some n to be your batch size, then you break this up into, so this is n and so on, right. So your m is the number of batches. So previously m was the number of replications, here m is the number of batches, which is simply n by m. Okay. So then you look at the inter-batch means and then use that for decisions. Okay. So that is the batch means approach. So you compute the, previously we had replication, right. So in this case for batch 1 you would compute the mean, then batch 2 you will compute the mean, and then use the these different batch means to decide whether there is where as to when you would stop counting the observations, right, or when you start counting observations and delete the ones before that. That is what this batch means. We want to, let me just put this rest of this down. Okay. So your batch mean is basically, so this is xi bar like before. So this is 1 over n, right. So this is, so here I is the replication, right. So I goes from so for every 500 customers compute the mean, right. You are not computing the overall mean like we did before. So not the running mean that is running, but this is just restart and then right, and compute for this batches at a time. So this is your so called batch mean. Then you compute the variance, right, in these means. So for a given value of n, we compute the variance, right, between the in terms of the using the batch means, and then you plot again with increasing value of n. So now you have a plot of so this is n and this is the variance of x bar for that particular value of n. So the point at which your variance starts decreasing is technically where transient state has finished and then steady state starts. So you basically will be going towards, if your means are all converging, you will be starting towards 0 variance, right. If your variance keeps increasing, then that is still where there is a lot of transientness in the system, and over a point of time as you start decreasing and going towards 0, then that is technically where, right. So it in ideal case should be something like this, I guess, when it starts decreasing and going towards 0. This is what you would like to see and say that at this point is where essentially your transient state finishes and steady state starts. Again, this we have to verify, but that is the basic theory, right. Though it is possible that you could be jumping up and down, right, have several of these little loops where you come down, then again go up, come down, go up, and finally go down to 0. But this is sort of ideally where, if you want to use this, this is the expected ideal behavior. System need not follow this particular behavior. It is possible that with there is so much of it's, if you have a scenario like this where you go up and come down, but then again go up and come down, the variance keeps changing, and finally at some point you really start going here. So this is where you should be having your transient state. This is still this is where the transient state ends, but if I simply say where it is decreasing, then I just cannot use that as the, right. So that becomes a local I guess local maximum. So the question is, what is the best batch size to use to compute, to say that, because you want to delete the initial data, right. So depending on the batch size, if batch size is very small, right, then so depending on the batch size, you will find that your if n equals n equals the number of observations and there is only one batch to deal with, in which case there is no variance to look at all, right. So you want to essentially look at computing the.
So each batch we are plotting.
Yeah, this is for each value of n. This is the value of n, the number of elements in the batch. You are trying to find out the optimal value of n, right. Yeah. So here again we can do independent replications or batched means. There is also something else called regeneration. So I have m independent replications with different seeds. of n plus n naught observations, of which, right, the first n naught are discarded, right. So, this is the default step that we done before. Then we compute the replication wise mean, right, this is replication mean. So, for replication okay, I, this is what we normally do, where you run it once, compute the mean, right. So, that is your xi bar, then you compute the overall mean. So, the overall mean So, just we like do before one replication per replication mean, then compute the overall mean like we have done, right. And then you compute the confidence interval. So, of course, when you compute the variance, right, the usual okay. So, now the question is the what do I control, right. So, I want to basically able to stop my simulation at some point and say I am done. The two parameters to control, one is the number of replications, right. I want this variance essentially to be very small, going close to 0, right, that is essentially what I want. So, that I know that the mean value I am computing is more or less representative of the system expected value. The other is to control the number of observations in each replication, right. So, this is how long should I run each replication for. So, which is easier with this approach, number of replications I can fix and say okay, run each for 1,000,000 completions, compute values, right, and then you start computing. So, run for first replication, second replication, third replication and so on, keep computing this variance of x bar, right, and then you would terminate either when the variance x bar goes to 0, it might never go to 0, right, it is possible that it might never go to 0, in which case you tell the system you have to have some sort of specification on what should be the confidence interval that you are looking for, right. Either you would say I have stopped after 10 replications and the confidence, right, so you can compute the confidence interval, right, with m replications. Would be this like we did before, right. So, x right, you can simply state that this is the confidence interval and then say I am done, right, whether you take it or not. So, this is not really termination condition, right, you are simply telling that after x number of replications I have come to this conclusion. Or what the driver auto terminate in that system tries to do is it tries to compute the ratio of this interval, right, this is a confidence interval. So, this divided by x bar, that should be some specified value that you want, right. I want to say that the 95% confidence, the width of the interval, right, or 1/2 of the width of the interval is no more than 5% of the mean. I can specify that as my termination condition, so that you keep running replications until I meet that particular value, right. So, if I have a specification size, right, if right, if this is less than say 0.5 or 0.05, right. So the interval is less than 5% of the mean, therefore you know that the mean plus or minus 5% is the confidence interval for whatever that you are specifying, right, for a given value of alpha. Alpha is specified, so if you look at the driver orthogonal it is specified 95 and you specify 0.05, right, that is the required width that you are looking for. If this interval value is in that mean or in that range that you are specifying, then you stop. Else continue with the number of replications, that is with the independent replications approach. So you need to specify the stopping criteria, right, you have to specify what variable or what metric that you are measuring and what confidence interval that you are looking for and what is the width of the interval that you desire to achieve. If all these three are met, then you say that okay, I am going to stop my simulations at that point. That is when you are varying the number of replications, assuming that each replication has enough samples to obtain some reasonable sample size. Right. So what actually our axiom tries to do is the other way around, the batch means approach. Where you simply run the simulation longer and longer and longer until this termination condition is met, but this autocorrelation between the data is a problem, right. So that you have to ensure that the autocorrelation index is fairly small or autocovariance. So here again I am running the system for, right, so n naught is this initial data which I am ignoring, then from here onwards there is a total of n plus n naught observations and then this I am breaking up into batches of size n, right. So I compute the batch mean, I compute the overall mean, compute the variance between the batch means, and then again I compute the same confidence interval based on the overall mean and the batch variance, right. And so we compute the batch mean, so m is simply n by so you will keep running for 500 more observations, right. So you keep increasing the number of batches, one more batch compute xi bar, right, then compute the overall mean, and then compute the variance of the means and the confidence interval. Okay. So you run it for 500, ignore the first 500, say that I have chosen to ignore first 500, then next 500, third 500 and so on, and finally like in the previous case my termination condition should be such that the interval width, the confidence interval width, right, the ratio of that to the mean, if that is within your specified requirement, then you say I am done, I stop, right. So that is the, but that assumes that system will go into steady state, assume that it will be convergent, right. Sometimes you will never converge, you try MM1 with a very large, with a row greater than 1, system will not converge, your queue will be, especially infinite queue, right, it will just keep building and your delay values will be increasing and so on, it will never get to steady state. So there you can simply say the system did not converge. Again we can say that I ran it for x amount of time, the variance never, right. So then again you would compute this, so your yeah, see this is where they missed out the square root of m, last time also I missed out, right. And here again choosing the value of n is non-trivial. 10 completions, 200 completions, 500 completions. So you know again if you get all the data, then you can choose different values of n, find out where your auto covariance is less, and then use that as the appropriate value, and then report the mean, because you are now reporting the mean value, right. So that value of n will also make a difference, but there we simply say okay, I think heuristically 500 completions is good enough to compute the mean for a particular system. So that is why if you look at it, I think you can specify the number of in your driver order terminal, it will specify 500 as the first parameter, saying number of completions at which is specifying what the batch with is. You can vary that, and so more larger the value of n, then more number of batches will have to be run to get steady state, right. So at the end of all this, the bottom line is that your simulation values, right, the output from simulation values, there can be a wide range of values possible depending on how you specify your n, your m, your width of the 95%, 99%, right, it is 10% deviation from the mean, okay. So all those things will finally give you one value. So you should never trust the number that comes from a simulation as the number for the system, right, it is just a representative number, and it mostly trends is what we look for when we try to compare two different systems with so much randomness in the system. Bottom line is, right, you cannot say the delay with the system is going to be exactly 2 seconds or 2 milliseconds, it just an approximate indication of what the system performance is going to be. Sorry, yeah, it's standard deviation. So my square root will go here. Now there is no form. If you look at the book has a table where your n varies from 1 to 256 to 512 and so on. Then they are also computing the auto covariance, and then wherever that is a very small value, they are saying that this is an appropriate value for the value of the mean. We simply just assume that it's 512, and hopefully nobody ever asks us to what you chose for the batch value, right. So that is that a little bit of arbitrariness is there. It is your results can be, yeah, that's what it said. So you can tweak your results whichever way you want by putting small batch numbers, you get better results. Your system is better than the others, you can do that. But somebody has to be questioning you, right, saying that what is the value of what is the batch size that you used, and does it make sense.
We take and we try to calculate that confidence interval on the standard deviation. How difference it will? What difference it will give?
This is for trying to terminate, right. So I am trying to terminate. So if I just run one replication, and if I am just computing one value of x, that is also there you are simply reporting that I ran it for, see there your value will vary depending upon the number of batches, number of customer completions that you see.
And I will keep calculating the confidence interval.
You can, that is the first approach that we saw, but there the termination condition is just simply arbitrary, right. You are saying that the termination that across the entire sample, you are saying that for the entire sample I could use the same termination condition, not in terms of batches, right. So your batch is basically size 1, right, batch size is basically 1, yeah. Where there you will find that between, if it is a single, right, between successive values there will be certain amount of correlation between successive values of your of the mean that you are trying to compute. That is what you try to avoid by going into larger batches. So that you are trying to say that if I go for 1024 customers at a time, then the batch mean I compute between two successive batches, there is not that much of correlation between the two. Okay, whereas on a per customer, there will be correlation between two successive customers leaving the system.
Suppose like to find out the optimum number of customers in system. So like first
optimal number of customers in the per batch or
system can handle. So if we calculated delay like 1024 we took, and next it gives directly 1024. It's big window.
No, this is calculating batch size or optimizing for the number of customers.
So suppose I'm calculating the delay.
Okay.
I'm saying if we keep increasing number of customers, my delay should not exceed some particular point. So I'm calculating that mean delay. It should have this particular value.
Okay.
If I have this batch means approach, like suppose my batch is 1024. So first batch will be 1024 and next batch mean it will calculate only after 1024.
Yeah, the second 1024 batch is mean is what you
calculate.
Yes.
And suppose my optimum number is somewhere between 1500 to 1600, but it will directly give me 1024 or 2048, something like that.
No. Wait, you are again talking of the batch size something being yeah. So then you can run if you, that's what this is post facto. You can sit and run this code for varying values of n, right, such that you find out which is the optimum value of n that you are looking for. You can do that, and then you will, based on that, you will report your batch mean and the corresponding confidence interval for that value of n. So what this says is that even the mean depends upon the value of n that you are choosing, and usually we fix the n if you want to be really making sure that there is correlation does not exist between batches, then you choose one particular value of n, and for that you can report. But most of the time it won't make that much of a difference, right? When you are in such a small range, you won't see that. Like if I told 1024, you will probably see from here to there is a big jump in terms of, and that too really depends upon how the system behavior is, right? There is a very complex system that you try to simulate. It is it's mostly just wishful thinking that okay, that there is not that much of correlation between the successive, right? Same thing with making assumptions about exponential or Poisson and so on. Those are all just convenient assumptions that we make. So here too we just say that in this particular simulation run I am reasonably confident that the values that I am presenting are representative of the system, right?
So nowhere in the termination condition we are comparing it with a theoretical value. We can have some termination
It's
condition.
not known for all systems.
For systems which is known, the theoretical like Q's at least we can calculate theoretical value.
If it is MM1, yeah, you can say that this is approaching the theoretical value, but if you have theoretical value, then why do you need the simulation?
To verify.
So many times, yeah, in some cases it is used as verification, but many times we are running simulations almost blindly. We don't have really closed form solutions. Even if it is closed form, the closed form has so much approximation, right, that is not really captured by the theory itself, right. So whereas the simulation can capture that better. So it is only asymptotic value that sometimes theory gives you, right. So it's not always possible.
What will be the effect of decreasing batch size? Will the termination condition occur fast?
If you make your batch size very small towards the end, right, your effective value of the batch mean that you are computing is depending on a small number of samples. So there so therefore since you are computing the overall mean, it is probably okay, but your each batch mean is only a very small set of samples, right. So therefore it might not be fully representative of the system final delay that you are looking for, the batch mean itself.
The termination condition, sir, that termination condition, we say, so if we have a smaller batch size, then that product will be less than 0.05.
Smaller batch size, okay.
So for a smaller batch size, we are likely to.
No, the batch size is only appearing here, but then I'm also this decreases, this increases, right? Your number of batches will proportionately increase, right? And so how will that affect your overall?
Smaller batch size variation can be large.
Yeah, within a smaller set of samples, right? So if you look at smaller samples, then the variation between subsequent batches can be very large.
So it doesn't affect the termination conditions. Varying the size of the batch.
It will affect. So you need to find out some optimal batch size, which is what I said. We simply take that. We think that 1000 samples is good enough, right? If you want to say what is the average GPA of a student on campus, I can get everybody's GPA, or I just take some 100 randomly selected students, right? And then we'll say there is average GPA is this, and therefore I think this is more or less what you will see if I keep replicating this over the next 100 students and so on, right? So ideally you should be taking 5 different 100 student batches. I find that the variance is more or less small, right, across these 5 batches. I say good enough. This is the mean of a particular class of this is mean for IIT students at large. That's what people try to do when they are trying to do your opinion polling and all those things, right? If you go to CNN and so on, right, when they poll 1,000 people and say Obama has got a rating of X, right, they didn't ask, nobody asked everybody. They might do that over few thousand batches, but they feel that that is good enough of a sample, right? And of course that's the, we leave that to the statistics folks as to how they handle that, but in this case that's what will happen. If your batch size is very small, the variance between batches will be large, so you want to capture a large enough sample size that between batches more or less representative values are there in all the batches. So I went and looked at those two methods that we saw last time, right, for the initial data for that transient state, right. So we saw this, there were 2 or 3 schemes, but we covered primarily IDS, and there is a moving average scheme which is very similar, which I have skipped, then there is the batch mean scheme, right. So IDS is with replications and batch means without replications. So I implemented both of them, and then I just looked at the numbers. So the way it generated numbers was, I had about 1,000 numbers total, right, just random numbers, and the first 100 numbers varied between. So this is some sort of, it is not exactly representative, you know, we could have used this with the MM1 system if you wanted to. So I had 100 numbers which was between 1 to 50, so there is more amount of variation. Then the next set of numbers were just 8 and 10, right, so I just varied it this way, so that I wanted to see that there is some sort of, right, sharp transient or sharp state transition from the transient state to the steady state, and so this I just fed into my program, which I hope is correct. So when I looked at the batch means, right, so in the batch means the idea is that you break it up into different batch sizes, and last time we kind of put a question mark saying, oh, what is a batch, cannot tell us what where the transient state is. So the idea is that wherever there is a definite decrease in the variance, right, it is kind of vaguely defined, wherever there is definite decrease in the variance, the batch size for which that variance, that change occurs, is considered to be the and up to that point is your transient state. So remember we had batch sizes varying from, so in that in this case I had say 1 to about 1,000, which is kind of silly. 1,000 is almost just only one batch. So I went from 2 to about 500 batches, you know, 333 batches and so on, and I plotted the corresponding variance, right. This is a batch size. This this diagram, this EPS file is there in Moodle now. I could not load the IDS file, so Moodle froze on me. So it definitely sort of, you know, it starts decreasing right away. It starts decreasing. Then the trend, if you see there, then again there is an increase, right. Then it goes up, and then it starts coming down. It kind of keeps going like this. It's kind of where you see. So, but the only thing that noticeable, because I know the value is 100, I notice that the after, so here it is decreasing and then increasing again the variance, but around this point after this exactly this is sort of, you know, 100 or so, then it decreases, but it never really comes back to the original thing. So this is sort of like your well, I guess that's not if I exclude this maximum, and this is where that maximum is taking place, right. So this is the, and with this we are supposed to decide that, you know, 100 is your I'm sorry,
What is the scale for variance?
Scale for this particular system, it started at 40 or 33 or something like that, right, because of this, depends on my set of input values that I have taken. Then it finally stabilized at 20, and then it sort of, you know, kept varying back and forth. So that's the, so again, so it says an approximation. The disadvantage here is that you need to know all the data values to actually make your decision, right. So that is the batch means graph. Then I did the same thing for IDS. So in IDS, if you look at it intuitively, what you are trying to do is you are computing the overall mean, right, and then as you start compressing to a smaller set of values like what I did here, then your overall mean will always be more than your actual mean, right. That is the way that my data set is. It could be the other way around, where initially it could be small values overall, then the values start increasing, in which case overall mean will be less. So when I simply plotted without that magnitude, right, just with the sign considered, then actually it started off with sort of, you know, yeah, some minus value, something 0, then it comes down to minus 1.1 and so on. So this is the IDS method, by the way. So in IDS method I am using this parameter L, right. So what I do is I exclude the first L elements and look at the mean of the next n minus L elements, that is my XL bar, and then I compute the rate of change respect to x bar, the overall mean, right. Overall mean in my case happened to be larger than the mean because of the fact that these values of 8 to 10 was the steady state values, initial values are all varying from 1 to 50. So it really kind of hard to say. So if we just plotted that value, in this case would negative of course, because x bar bar is always greater than x bar, but the nice thing was that it sort of stabilized like this. So and because of the fact that I had induced, right, my data was cooked up so that I have very little variation after the 100th sample, it was all just 8, 9, 10 and so on. So therefore that the means around, right, if I exclude the first 100 values, all the values are between the range 8 to 10. So therefore the mean will be sort of more or less stable, rate of change is going to be less even if I add or drop more samples.
Something related to what we say the warm up time that we give the simulation.
That's correct, yeah. So we just want to exclude, I want to drop that first 100 values. Only thing is I do not know where that sort of transition occurs. In this case it is a very sharp transition. I could have been little bit more, I could have made my number tandem generator such that I have 1 to 100 is 0 to 50 and then I bring it to 50 to 30 and 30 to 20 and so on. But anyway, so depending on your set of values you will get some sort of indication. So that is just wanted to because in the book you simply said it goes from 0 to positive, and that is not necessarily the case because it depends on the values of your x bar and x bar bar unless you are using magnitude.
No sir, but once we are taking the mean, at that time the starting value will consider will just remove the.
You are going to remove, you are right. Basically what you want to do is you want to delete first L values, you want to find the value of L where the mean is sort of stabilizing, right. The change in mean is or the change in mean is sort of less as you from this point onwards, because you have a smaller window of values that you are operating at, and that is assuming. So again two things to consider. One is if I am, in my case I simply had individual numbers plotted. I could also have computed the running average, which is what you would do in the case of average delay, right. If you are computing packet delay in a system, it is always the running average, that your EFT is what you are computing with every new sample you are updating your EFT, in which case this sort of large variation will not be there, because from 50 I will not go down to 9 and 10 because it is no longer average. So those things we can just play around with, but that is I just wanted to see with this set of non-averaged values, do we get some sort of indication, and it so happens that there is some indication that you can use. So the closing statement is that to find out the transient state, the only disadvantage here is, or one disadvantage here is that I need to know the entire set of values. So during simulation how do I figure out that I am going to start terminating, I won't consider values up to this point onward, right. When I am running the simulation I want to say I have reached steady state, I am going to start counting steady state packets. In all these cases I need to know all the values from 1 to m, right, or the entire sample set I need to know. So that is a little bit harder, right. So how do you do that? During simulation if you want to simply say I figured I have entered steady state and therefore I will not, so you can.
You run 2-3 simulation, usually you come to know okay after say 20 runs then you give that period as the warm up period and then start. Yeah,
so you run one and then you find it out and then use that for the subsequent, that is okay. But if I still want to do it within the simulation run, then well I guess you could sort of compute the, again with the window, right, you compute the variance of your data values achieved so far, and then as your variance starts sort of decreasing, right, or then there is some sort of stability in your either mean or variance is what you would look at, right, I think, so that your values are within some sort of this range here, and you find that window for variance values is within plus or minus some threshold, then you can say that my system is more or less stable. But that is, we have to be absolutely sure, right, that there will be no such changes, because what happens is if you look at a system like an MMQ system, MM1 system, right, if you look at for example the number of customers in the system, right, you will have this sort of cyclic periods. This is simply n, the instantaneous n value. If I use n as my value, then the system will increase, so customers get added, then they get serviced, then they get serviced, and there is always the possibility when depending on your row value, if the row is sort of interim, right, you will have in some periods of time where there is absolutely no customer in the system, right, because this is the probability system being idle, which is 1 minus rho, right, this is your P naught, that there is no customer in the system. So you will have, depending on your value of rho, some sort of right definite periods where your system, so in this case then if I compute the variance then it will be sort of warped, right, not exactly what I want to do. So in bottom line is that for this initial data deletion it is a little bit harder to figure it out runtime. So mostly we just from some prior knowledge just drop the first few hundred packets and then just include the rest, and then use that for your overall mean calculations. Okay.
It is only useful, sir, if our calculation is taking a lot of computation time.
Yeah, no, yes, or no, or you don't want the transient state to affect your steady state computations, right? If you have basically outliers, too many outliers are there, because all those outliers when they get included affects your calculation of the mean.
What I'm saying, sir, if you take little bit, more values for dropping also, it will not affect much, because once it has reached some steady state, if you miscalculate 100 or you calculate 110, it will not make much difference.
Yeah, those minor variations won't make a difference. Yes, if there is a definite, yeah.
Always take more, whatever.
Yeah, so you have to run the simulation for longer. So the best way to say is, okay, I am stopping 100, okay, I'll just instead of 1 million run for 2 million, so that even if I make a mistake in the earlier states, I still have enough of data samples from the remaining part of the simulation. So we can do that.
It's initial data deletion.
Yes, we are just trying to look at if there is something we can do to definitely figure out where the transient, but sometimes there are needs to actually look into this transient state analysis itself, right. So if you really want to know what is the Q structure in the transient state, I think in circuits you probably would need to look at the transient state behavior more than steady state behavior, right. So in that case then you want to actually understand, see where the transient state stops, so you are more interested in this, you do not want to make a mistake in, right. If you are only steady state, then that is fine, I can run it for long periods of time. If only transient state, then you cannot afford to, right, have too much of leeway in where the transient state ends. Okay.
You can also have a trace file. At the end of the simulation, we can see the trace file, and then we can find out as to at which point the transient.
Yeah, that's what all these our IDS and batch means. Sure. All of them are based on calculating at the end of it. Like NS2 gives you a trace file.
So we are saying that we want to calculate it on the fly.
Yeah, during the simulation, like in the case of termination, you are doing it during the simulation, right. You are running the simulation, you are computing your batch means, and then you are finally saying that my batch means are kind of stabilizing, therefore I do not want to run any further. So similarly, you want to do an online decision as to from now on I will start collecting data for steady state, right. So I want to see, I know now that the system has moved to steady state from the transient state. That is what we are trying to do. So and so last class we were talking about the termination condition, right. So the last thing in termination condition is that, so we can use batch means, that is what the Axiom program tries to do. So you use batch means to terminate one given simulation, but that is not adequate. So you would also, right, so run to terminate right, use that batch means method. Of course the other method is also, right, and then couple that with that should be absolutely safe, because this batch means also tries to ensure that between the batches there is no correlation, right, that they are independent batches, so we can use them. That is one way of looking at it. The other way is to simply run multiple independent replications and then right, so run it once, stop it when the simulation is stabilizing, then run it again for small number of seed values, right, depending on how much variation that you see. So it is always a trade off between time and
We are terminating based on the confidence interval, like the MM1 QB which you have given, you have put that 90%, but still you are passing that max time.
Yes, because I wanted it, because when I give a very large value of rho, system will never converge, and in which case if what happens, delays will just keep on increasing, right. If you have infinite Q and rho is very large, your Q size keeps on increasing because you are adding more packets, especially if even we can even put rho greater than 1 if you want to, but even rho close to 1 you will find that the delay value will no longer converge, delay will really start shooting up, in which case it is a race, in which case you will never get convergence. So you might be sitting there waiting for a program to end, might take a very long, well it might never happen. So there is a way to actually say that it diverged and then stop at that point. So that is why we are giving back. Yeah, that is why just as a cop out we are saying that, okay, I run it for whatever 2 million units and I will simply report the value for 2 million, this is the value.